Thank you. So, so today I will give my third lecture, which will be about regularity of optimal transport. It's a topic which, it appears a lot. We even saw that yesterday in some lectures where even in the discrete situation, you know that if the transport map has some regularity, perhaps some uniform convexity or bounded oscillation, then you can make maybe better bounds or better approximation bounds. So, it's a theoretical tool, but at the same time, it appears a lot to know something about the structure. So maybe I will start from for those of you who are not familiar with it, I will start really from the beginning. So let me set it up. I will do it in the flat case, but there is a lot also known in the non-flat case. So let's say we are in the flat case Rn. I will denote by F the density that our source density, and then by G the target density. And so in optimal transport, what you do is that you want to find a map that minimizes the transportation cost and transports F to G. So the regularity theory, depends a lot on the cost. So regularity of OT depends on the cost CXY. And in general, truth is, if you don't take the quadratic cost, it's usually rather bad. So I will focus on CXY x minus y squared. So in this case, we have Brenier theorem from 87, Comtrendieu, 91 published, which proved that in this case, there exists a unique T optimal, and T is the gradient of phi, where phi from Rn to R is convex. Okay, so there is this map which minimizes the transportation cost, and it's the gradient of a convex function. We have seen yesterday, for instance, that the fact that it's a gradient of a convex function is a very important property because, for instance, it was very fundamental for me in the proof of the supersymmetric inequality, because then I had properties on the gradient of the transport map.
How the convex function, what is the smoothness? Because I don't know how
now, so far it's just convex. So the convex function is locally Lipschitz. But then which means that the transport map is locally bounded. So not much so at this level. So when Brenier proved it, it could just prove this. So to be precise, Brenier had to assume that the density were bounded or compact supported, or maybe had some moments. And then, let's say, without assumptions, this was done by McCann in 1995. So if you just have densities which are without moment assumptions, then you can still construct this map. But okay, that's a detail. Okay, now what about so how can you try to understand, how can you relate this phi or this T to F and G? Yesterday I hinted that when I say that the Jacobian of the transport map is constant, when the density are constant. So let me try to derive an equation now. So we know that T is a transport, so T transport means that the push forward of F through T is equal to G, which means, by definition, this means that for every test function psi, the integral of psi of T of x, f of x dx over Rn is equal to the integral of psi of y, g of y, dy. So this is the change of variable formula, which is just by definition. So T is a transport map if and only if this is true. And now, once you take this identity, and now you assume, so formally, you can assume that T is a diffeomorphism, then I can say that Y, I can take Y equal T of X, so change of variable. Then the volume element dy will be the determinant of grad T at X times dx. So I substitute, so this is the change of variable form, and then I get psi of T of X, G of T of X, determinant grad T of X, dx. And you see that this equality has to be true for every psi. So for every psi, now I have the same function here. This is the same as this. So if these two integrals are the same for every psi, it means that f of x is equal to g of t of x. So these two have to be the same. So we arrive at the following formula: determinant of the gradient of t of x equal to f of x over g of t of x. But now we remember that t is the gradient of phi. And then I can substitute, and then I get the determinant of the Hessian of phi at x is equal to f of x over g of grad phi at x. And I don't even need now to put the modulus, because phi is convex, so the Hessian is positive definite, and so the determinant is non-negative. Right? So this is a non-negative definite matrix. Okay, and now this is called, so this PD is the Monge-Ampère equation. So it's, for those of you who are not familiar, it's the nonlinear version of the Laplace equation. So the Laplace equation would be like the trace of the Hessian equals something, and Monge-Ampère is the determinant of the Hessian equals something. And out of this PD now, we would like to say that if f is nice and g is nice, then phi is nice, ideally. So the kind of question is, f and g nice, whatever that means, does it imply that phi or grad phi is nice? Whatever that means. Okay, so this is, you see, at the end of the 80s, Brenier proved this theorem. So here came the connection to Monge-Ampère, and Monge-Ampère was actually a rather well-studied PDE. It's a PDE that has been introduced way before optimal transport, and there was a decent regularity theory. So of course it was natural to say maybe we can apply the regularity theory of Monge-Ampère in this setting. And however, there are some catches here, because you immediately see that even to write this, I had to cheat a bit, because I had to do a change of variable formula, which in a sense looks like the chicken and egg. I have to assume that the T is a smooth map, a nice diffeomorphism to do this computation, to then find a PD that I want to use to prove that it's a smooth map. So it looks like I'm cheating a bit. In fact, I was cheating. In which sense? Well, so in the beginning of the 90s, Caffarelli was an expert in nonlinear PDEs, tried to see how, through Monge-Ampère, he could prove something of optimal transport. So in 91, Caffarelli did the following. He said, OK, let me see what I can really say about optimal transport. And then he made immediately the following observation. He said, OK, let me consider this case where f is 1 inside a disk. OK? So I'm in R2. Let's do n equal 2. And you take uniform density inside the disk. Very nice. And now let me take as g the uniform density inside two half disks. So g equal 1 and g equal 1. I just take this disk, I cut it in two, and I separate. In this case, the transport map is actually rather easy to find, because what we'll do, we'll just cut into this disk, and then the top part moves up, and the bottom part moves down. So it's just a translation one translation here and one translation there, with a sharp separation. That's the optimal map in this case. Not difficult to prove. So this map T, you see, F is as nice as you can think of. It's 1. G is 1.
Normally they shouldn't have the same support.
No. 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 They could be anything, right? I mean, they are just two probability density in a REN. But then they could be positive in some region, 0 somewhere. So this is the first situation where we have F equal 1, G equal 1, just on different domains, of course. And the T here is, so the transport map T is not continuous. So the gradient of phi is not continuous, which means phi is not C1. And then you could say, okay, well, that's clear once you look at this, just because by topological reason, a connected set cannot be sent to a disconnected set via continuous map. Image of connected set is connected. So just the map cannot be continuous, just topologically. And then you could say, okay, then what if I assume that the target is connected? So here you see the support of F is a disk, but the support of G is a disconnected set. So then you could say, you could consider the second example, which is this. So I take the same, almost the same picture, and then I add a small bridge in the middle. Okay, so F is 1, and I consider G equal 1 here, but then I connect the two disks with a very small bridge. Okay, maybe I need to normalize a bit, maybe shrink to make the volume to be the right one, right? But I think you get it. Then I have maps T epsilon, which will send something, somehow this to this. And what happens here is that what Caffarelli proved is that if epsilon is small enough, T epsilon will still not be continuous. So what you can think is that at the beginning, like if I take, essentially what happens is that if I take 2 points here and here, this point will still be sent more or less here, and this point will still be sent here. So you don't have now a sharp separation, but there will still be discontinuities here and there that will survive. Yeah.
Is this a property of the optimal transport or like any transport between?
No. It's the problem of the optimal transport. So well, it depends how you take it, but technically at this moment, let's say I could smooth this out, and there is no topological reasons why I cannot find a diffeomorphism that maps one to the other. So I could, maybe shrink here and make it very tiny. So it's really that the optimal map does that. And optimal, it's if and only if you are the gradient of a convex function. So in a sense, if you look for a gradient of a convex function that does that, then you will never find a continuous map. Okay. Maybe let me erase this. So this example looks, okay, before I tell you what Caffarelli did, let me just tell you that actually you could say, okay, what if this is just because that bridge is so thin? You're cheating, come on, it's so far from, it's almost disconnected. Okay, then a former student of mine, Yash Javeri, in 2019, actually showed this example. You take F equal 1 in the disk, and now you take, sorry, in the square. The square doesn't play a huge role, but it's just convenient. And now what you're gonna do, that you take this domain, this same square, and you put a small dent like this. So let's say this has length 1/2, and this has length epsilon. And now you take constant density G equal 1 inside, or whatever, normalize. So you see, I'm just taking the square and just pushing it inside on one side slightly. So this is Lipschitz domain with a very, very small Lipschitz constant, almost flat. So this map will be very close to the identity map, because if epsilon goes to 0, the optimal transport will be the identity. And for every epsilon positive, the epsilon is never continuous, in this example. So in reality, discontinuity is really actually something rather bad. I mean, you can produce it instantaneously, even if you just perturb. So the reason why you can do it is because this is a Lipschitz deformation. So if you took a smooth deformation of the boundary, you will not be able to produce this immediately. You need to push a bit. But because I'm allowing to create this kind of corners in my deformation, then you can destroy immediately the continuity of the map. So,
Question? Sorry.
yes.
So these examples show the optimal map is bad, okay? Or whatever, it is what it is.
It is what it is.
We have to live with it.
We live with
So
it.
are there, of course, in the first example, maybe not, but the other two, if you go a little bit away from the optimal cost, can you make them continuous again? You know, if you work a little bit, you know, the cost is a little bit bigger than it should be.
Well,
I mean, not
it depends on whether you are consider what is it in a perturbative regime or what. I mean, it depends.
Yeah, so I'm allowing transformations which do not achieve the optimal cost, but something a little bit bigger.
Right, but then are the domains close to each other or something or
I
not?
take the same domains, the same problem, and ask
That one.
Yeah, for instance.
Well, there then yes, but this is like almost very easy, right? Because it's just, you see, for epsilon equals 0, the optimal map is the identity, and then I can just deform it smoothly to be a diffeomorphism, and then automatically it will have very low cost, almost optimal cost, because it was very close to an optimal map. So in fact, you know, kind of robust, these problems, you can always make them robust, but I think the message here is more like, you see, in that situation, you see, the optimal map is very not discontinuous. So everything which is almost optimal will be close to the optimal map, and then you will never achieve some continuity. I mean,
Okay, so the continuity bound is really essential. It's not just a little epsilon.
yeah, so in a sense, the moment the cost is almost optimal, it means that, you know, in many points, you have to be very close to the optimal map in some sense. And then once you are close in many points, and there is a non-trivial amount of discontinuity where, you know, a lot of points here are mapped here, and a lot of points there are mapped there, then automatically I'm not close enough. You'll have to have similar properties of.
So at the moment, example 2 is my favorite example.
With this one.
Yes, because I think there you can maybe still perturb a little bit, but there you probably
Well, there I think what this is showing you is that if you look at the optimal map, you can destroy instantaneously the regularity. This is more like the fact that, you know, you can have transport maps which are very discontinuous, but I'm showing there that this regularity can be destroyed also rather quickly if you allow Lipschitz deformation of the domain. Not with smooth ones. For smooth ones, we know that it cannot happen, but for Lipschitz ones. Okay, now let's take these 3 examples, and let's try to get a positive result at least, because, you know, otherwise life would be too depressing. Or maybe you could also, will be nothing to do. Now, actually, there is something you can do, and that's actually what Caffarelli did. I would say between 91 and 96. The first thing he proved is that if, so let me assume the following. So let me assume that so let's take omega is the region where f is positive. Lambda is the region where g is positive. So these are like almost everywhere. So I take the region where f and g lives, okay? And I'm going to assume that given this, that f is actually between 2 constants, let's say 1 over lambda and lambda, inside in omega, and g is between 1 over lambda and lambda in capital lambda. So I have these 2 domains where f and g are neither close to 0, neither close to infinity. So these assumptions are natural because I want kind of this ratio f over g to be neither close to 0 nor to infinity. I don't want vacuum and I don't want huge right-hand side. So I'm going to assume this. And now I'm going to assume also that lambda is convex. So the target is convex. So this is not convex. that ones are not convex. Then the transport map T, which is the variant of phi, is locally Holder continuous. So it's continuous and it's actually Holder continuous for some alpha. In addition, if f and g are smoother, let's say ck alpha or c infinity, then t, which is the gradient of phi, will be ck plus 1 alpha. So maybe alpha is different, beta is not this alpha. So once the target is continuous, then the map is actually continuous. So once the target is convex, the map is continuous. And then if the densities start to get more regular, the map will be more regular. And this is the same regularity as for the Laplacian. So see, if f and g have some regularity, phi gains 2 derivatives. So gradient of phi gains 1 derivative, like for the Laplacian. If you have right-hand side in ck alpha, ck beta, the Laplacian phi is ck beta, then phi is ck plus 2 beta. So 2 derivatives more.
Continuous inside the support.
So these are continuous inside the respective support. So this is continuous inside its support, and this is continuous inside its support. And then the map will be continuous inside. This is the local regularity. So local means let me give local means that it's not up to the boundary. Right? So for instance, omega could be this, lambda would be this, or omega could be disconnected. And lambda is this. Then you have the map T, or the map T. And let's say in this situation, the map is very smooth if the densities are nice, because the target is convex. But it's smooth inside, so not necessarily up to the boundary. So the regularity could degenerate near the boundary. If you don't like the regularity to degenerate, then you need to assume also that this one is convex. So once you assume that both are convex, then you get a nice diffeomorphism between the domains. So, so here I just stated the local regularity. Maybe I add here, if omega also convex and smooth, one can get global regularity. Okay? So it's like a smooth diffeomorphism between two domains. So like if you give me two smooth convex sets and nice density inside, then the optimal transport will be smooth and as nice as it has to be, as it can be. Okay? So this is a bit the picture of the regularity. Let me just mention that the theorem by Caffarelli here, which is hidden essentially in this assumption, because I'm assuming f and g to be bounded away from 0, but they have to be probability densities, then automatically these domains are bounded, because you don't have a probability density which satisfies that. So you could ask yourself what the case of unbounded domains. So the theorem doesn't cover unbounded domains, which maybe is annoying sometimes because maybe you think about Gaussians or densities which have support the whole Rn. Technically, this theorem doesn't cover it. And only recently we found, we managed to extend this to the case of unbounded domains. So the theorem is exactly the same. If it's convex, this is true. But the assumption, this has to be weakened to some local positive assumption. So like this is satisfied on compact sets, something like that. I mean, the only way you can, yes?
Sorry, so the inequalities for f and g, I think I'm confused with those inequalities. So that one implication is that f over g is less than 1, or lambda?
No, f over g is bounded by 1 over lambda square and larger than, is bounded by 1 over lambda square and larger than lambda square. Oh, sorry.
Yeah,
I switched up, sorry. Of course, it doesn't make sense. Either lambda is greater than 1 or is smaller than 1. I'm sorry. Thank you. Of course. Yeah. It makes sense. I mean, lambda cannot be at the same time larger than 1 and smaller than 1. So lambda is a small number, 1 over lambda is a large number, here's a small number, large number.
Both 1.
Yeah, well, which is still true, but it's not such an exciting theorem, right? Only for g equal 1. Sorry, thank you. So does it make sense, all this? So the philosophy is that if the domains are not convex, forget it. If the domains start to get convex, you can get something. You may actually ask, and that's also a very beautiful question, perhaps if the domains are not convex, maybe you can still prove some regularity, perhaps outside some set. So for instance, in Caffarelli theorem, in Caffarelli example, you see, once you remove this line, this map is very smooth outside of this line. Or also in this other example, the one with the bridge, the small neck, once you kind of remove this discontinuity region, the map from here to here is a diffeomorphism. But you have first to remove these cracks. So a theorem that I proved now 15 years ago says that there exist two sets sigma, let's say sigma, so let's say this is omega and this is lambda. Sigma omega and sigma lambda, both of measure 0. Compact, well, closed set, such that the transport map from omega minus sigma omega to lambda minus sigma lambda is smooth if f and g are. So you can still get Caffarelli theorem for every domain, but you first need to remove a closed set of measure 0 here and here, and then you have smoothness. So that's true.
What would be sigma lambda in this case?
In this case, there is no sigma lambda, but maybe there is sigma lambda. So what could happen? So in this case, there is none, but maybe I can just complicate my life by adding. I can do it backward, right? So omega could be. I mean, the easiest probably here would be to add another component to omega, right? And then I need maybe to break it. So maybe what happens in this situation, I don't know, this goes here, but then this goes up to here, and then there is a crack, and then this part is mapped here. Sorry, this is more the other way around. So there is a symmetry between the two problems. You can look in this direction, you can look in this direction. So what I'm proving is that it's a smooth so once you remove these two sets, you have a diffeomorphism, which is really a smooth change of Barrow. Okay, now, so far, I haven't discussed applications. I would like to discuss some applications, actually, of regularity. So a theorem that I like a lot is due again to Luis in 2000. So Luis in 2000 looked at the following case. He said, let's take f to be a Gaussian. So the standard Gaussian. And let me take G to be, let's say, something like e to the minus w of x. So still some density, let's say, well, which will have to satisfy some assumption. Which, let's say, something of this form, but maybe not exactly quadratic. And then let's look at the transport map between them. See, can I say something about this? Maybe the Gaussian is special. So T is the gradient of phi. So I can write my equation again. Determinant of the action of phi equal Cn e to the minus mod of x squared over 2 divided by e to the minus w composed with the gradient of phi of x. Okay. Now you look at this. There are a lot of exponentials. Let's take a log. So log that of d squared phi is equal to, okay, a constant. Log of Cn, not very important. Log of this gives me minus x squared over 2. And this gives me w of grad phi. Okay, so this is my new PD. And then now the key fact, so this is a nonlinear PD, right? Because it's log of the depth. But what you can ask yourself is, can I get out of this a linear equation for the second derivatives of phi? So what you take this, so now you're going to fix a direction E on the unit sphere, and now you compute the second derivatives of your PD. So you take this equation, you differentiate it twice in some fixed direction. Okay, say E equally 1. So you differentiate twice in the one direction. So, of course, this will get, so you see here there are second derivatives, you do it two derivatives more, you will get 4 derivatives of phi. But you will get, so it will be like Hessian, so when you do it, you will start to get stuff like that. So maybe let me do it in an abstract way, it's easier to see. So this is a function of the Hessian. So f of a matrix. You differentiate it once, so you have d1 of f. Forget for a moment the left-hand side, the right-hand side of the Hessian of phi. This is the gradient of f, a Hessian of phi, times the Hessian of d1 phi. And now you differentiate one more time. So I have to differentiate this product. I will get the gradient of f at the Hessian of phi multiplied by the Hessian of d11 phi plus Hessian of f at Hessian of phi multiplied by Hessian d1 phi, Hessian d1 phi. A lot of indices that I'm a bit of writing this piece, right? So I'm just doing chain rule. Okay, so this term, so if you call this, this is a matrix, if you call this matrix A of x, you see this is just a linear PDE. So it's like Aij dij of d11 phi, this first term. So it's a linear PDE for the second derivatives. And now you have this term that looks, if you write it even explicitly, it will not tell you much. It looks horrible. I don't know, it's a total nonlinear term. But there is a fact that it's maybe some of you are familiar with that if you consider the space of symmetric positive definite matrices, so you take the space sim plus, so these are the matrices A symmetric in Rn, A non-negative definite, and then you take the map that to A associates log that A, this map is concave. This is a concave function. Because it's concave, this is my f of A. Then because it's concave, its Hessian is negative definite. So this term that you don't know what to do with has a sign. So you will not be able to write a PDE for this, but you will write so these second derivatives don't solve an exact PDE, but it solves an PDE with an inequality, because this time you just throw it away. And now if you use this, you have a PDE for the second derivative, you ask, there is some maximum principle trick, and then you prove the following theorem. So theorem, if the Hessian of W is greater or equal, let's say I will do the simple case as we stated it, is greater or equal than the identity matrix. The theorem is much more general, but then the transport map T equal gradient of phi is 1 Lipschitz. So it means that the Hessian of phi has all the eigenvalues bounded by the identity matrix, if you want. So there is an upper bound on that. If you change maybe the constant, if you put an alpha, you will get something like 1 over square root of alpha Lipschitz or something like that. So and then you will get that the Hessian is bounded by this over square root of alpha. So let's say, given a bound on the action of W, you can transport this, you can imply then a bound on the action of the phi, which is, but the action of phi is like the gradient of the transport map. So it tells you something on the gradient of the transport map. So the map is actually nice. Okay? So this kind of result is actually rather remarkable because this constant alpha, it's totally dimension independent. So you get a theorem which has nothing to do with n. There is no n appearing, which is not so usual in PDEs. Usually if you're in the higher the dimension, the worse things get worse. But here it's a totally dimension-free bound. So as n goes to infinity, this remains uniformly true. Okay? So let me show you an application of this. This is it's a simple application. There has been many applications of this theorem over time, but the simplest one is the fact that, so for instance, corollary, if the action of W is greater or equal than the identity matrix, then e to the minus W satisfies the same Poincaré inequality as the Gaussian. So what does it mean this? It means the following. So let me call gamma n the Gaussian measure. Then it's known that, let's say, for every function psi with average 0, you know that the integral of psi square gamma n is bounded by constant, which I never remember if with this number, maybe it's 1 now, grad psi square gamma n, something like this. So you have an inequality, Poincaré inequality, where the gradient controls the function in L2 with constant 1. And now the claim is that if you give me a measure with this property, e to the minus W, where the action is greater than identity, the same inequality is true with the same constant. I mean, this was already known, but the proof now it's very direct because you can just use optimal transport. How do you do this? So you think, so this is my Gaussian measure. This is my gamma n. Here I have my e to the minus W. And I have my transport map, grad phi, t equal grad phi. And I need to prove that for every test function here, I have this property. So now I given psi living here, integral psi e to the minus W equals 0. So given a function here that lives here, psi, I'm going to build a test function here by composing with the transport map. So maybe I shouldn't call it psi. Let me call it, so phi is used, h. Define psi to be h composed with t. See, psi is here. My function, sorry, h is here. So I have to define a psi here. I just compose with the transport map. So this pulls it back there. Then, by the push-forward condition, the integral of psi times gamma n is the integral of h composed with t gamma n. Now the push-forward tells me that this is the same as h e to the minus w, so this is 0. So to this function, I can apply the inequality, and I get that the integral of psi square gamma n is bounded by the integral of grad psi square gamma n. And now I just remember what is psi. This means that the integral of h squared composed with t gamma n is bounded by the integral of gradient of h composed with t square gamma n. And now we'll do chain rule here. I mean, it's the kind of proof that you just, once you know what to do, you just plug it in and you compute. So you just compute here, and then you get the gradient. By chain rule, this is gradient of h composed with t times gradient of t. So you get h squared composed with t gamma n is bounded by the integral of gradient of h square composed with t, gradient of t, square, the gamma n. And now this is bounded by 1. by Caffarelli theorem. I mean, this is the operator norm that you have to put there. And so this is bounded by the integral of grad h square composed with t gamma n. And now the push forward condition, this is the same as grad h square e to the minus w. And by push forward, this is the same as h square e to the minus w. So I just plug it in and I change variables. And the only term that was problematic is bounded by 1 because of Caffarelli. So this was an example. And this example actually motivated a lot of work in the idea that optimal transport could be a way to transport properties between different densities, in the sense that there is a density which is nice, the Gaussian, on which I can prove stuff. There is a density on which I know nothing, and I would like to prove stuff for this density. So if the transport map has some nice properties, perhaps I can transfer properties from one to the other. Now, this workshop is about non-commutative optimal transport, right? There is a non-commutative work. So there is a situation which is very non-commutative, which is when you look at matrices. So matrices don't commute. So I remember when I was spending a semester at MIT 13 years ago, I was discussing with Alice Guionnet because she really wanted to understand whether there was any hope to adapt these kind of ideas to transport. So she's working on random matrices. And she said, I would really like to do transport between matrices. Just, I don't have a notion, a good tool to do non-commutative optimal transport. And we thought a bit. At the beginning, we tried a bit directly on the matrices, but we couldn't really figure out an efficient way because, of course, you have a theorem in mind. It's not only that you want an abstract theorem, you also want she had in mind very clearly what applications she wanted. And then in that case, in some sense, we had to quickly give up on that, just doing an abstract thing on matrices, but we said, okay, let's focus on the eigenvalues. So if you are in random matrices, the situation is the following. You have a matrix with random entries. Think that you have a very large matrix, n by n, symmetric, let's say. And let's say that the entries here and all here are all random, identically distributed. And let's say the best case is when they have they're like Gaussian. So this is like you can think of this as a probability distribution in the space of coefficients of a matrix, right? So you have your coefficients that are distributed according to a Gaussian in a high-dimensional space. You have, this is like a Gaussian in R n cross n plus 1 over 2, right? Because you have all the space of all the coefficients, the dimension of the symmetric matrices is this, right? So you have these huge Gaussian densities, and then, so this is one model that is very well known. With Gaussians, you can do all computation you want. There are explicit computation. But now you say, okay, what if I tilt and I twist a bit this model? A bit as I was doing there. I go from the Gaussian to something which is not Gaussian. Can I still prove that some properties survive? And I would like to do it with some transport map. The problem is that really when you do this, you don't have to work at the level of the coefficients, you have to work at the level of the eigenvalues. So if you take a random matrix like this, Gaussian, you see, this is a Gaussian. But now you look at the law of the eigenvalues. So the eigenvalues are also random. They are real because it's symmetric. And there are n of them. And the law of the eigenvalues is something like e to the minus sum of lambda I squared over 2, d lambda 1, d lambda n. So a nice Gaussian law. But there is an interaction term, which is e sum I and j, a constant beta, it depends on the model, but let's say then you have log of lambda I minus lambda j. So there is an interaction term that it's very singular, it's a log, of the difference on the eigenvalues. Okay? So suddenly, although you started with the Gaussian density in the coefficients, you have a very non-Gaussian distribution here, because this is nice, but this is terrible from the point of view of this theorem, for instance. It's not at all of that form. So just maybe as a comment, when you look at this, it looks totally crazy, but you see what this is telling you in a quantitative form, if you think the distribution eigenvalues is measuring the fact that with high probability, the eigenvalues are all distinct. So you see, if you give me a matrix at random, a matrix at random will ever have equal eigenvalues. So the more the eigenvalues get closer and closer, the more the log term will be strong. And this is essentially, it gets stronger and stronger the more eigenvalues get closer. So the probability of having a measure with 2 eigenvalues very close is small, but then if you want 3 eigenvalues very close to each other, it's even smaller, and so on. So it's quantified in that density. There is this log term which is measuring there is a sort of repulsion between eigenvalues in a matrix. So what you want to do in reality, the goal that people focus in random matrix would be to replace this quadratic term with something like W of lambda I. So this is the goal. The only problem is that I still have the same interaction sum of the logs. So this term doesn't change, but I have now a W potential. These are what is called beta models in random matrix theory. So you see, when you look at the level of eigenvalues, it looks almost like Caffarelli. The only problem is that they have a horrible interaction term, which just if you try to make any proof like that, will break down completely. So now you could ask yourself, and this is a bit in the spirit of what has been asked before, what if I don't look for an optimal transport map, but maybe I look for something which is almost optimal? That's what we did there. We gave up on optimality. Say, why do we care about the optimal map? Maybe it's enough to have something which is optimal in some sense. And the way we did it, and I think, yeah, I have almost out of time, was the following, is to say, okay, I have this bunch of, so I have my 2 probability densities, the Gaussian one and the other one, right? So they live in some high-dimensional space, Rn. So I have my lambda I here, and then I have my, I don't know, lambda I tilde here. These are the, I mean, just to change, just to distinguish, before I was using x and y. I don't know, now I use lambda I tilde. And I want a map here, depending on n, on the dimension. And the idea here is to say, okay, let's think a moment, what do you really want? We want a map that has to provide us with a change of variable. That's the goal. So that then some integrals, we will have now, the goal is later is to compute integrals of eigenvalues. So the goal is that you have integrals of functions of the eigenvalues integrated against these measures. So this is, let me call this mu gamma, and this is mu w. I want to compute integrals of this form, d mu w, of lambda I. And this depends on n, okay? So I want to compute stuff like that. I don't know how to compute it. I want a map that allows me to do a change of variable so that the integrals is performed here, where I don't want to do the computation. But then, of course, the price to pay is that the map will appear here. So this will be the same as the integral of psi composed with the map, d mu gamma n lambda I. So unless my map is nice enough, I will never be able to do anything useful. So what do I want? I want a map which is a change of variable and is nice. And usually, there is a third information here, is that you only care about the problem as the number of eigenvalues goes to infinity, because usually you already look for asymptotic properties. So I don't care this for fixed n, I only care this as n goes to infinity. So what we did was to say, okay, let's do it by steps. So what do we believe that this map should do? The eigenvalues at first order shouldn't interact. That's hidden in that fact. The interaction should come as a higher order correction, because at the beginning the eigenvalues should interact. So let's look first for a map. My Tn, I will take it as the first component should be diagonal. So Tn of lambda 1 to lambda n, it should be something that at the first order is very easy. It's just a map, a T0 map of lambda 1 and then T0 of lambda n. So a block transport which just maps the first eigenvalue here to the first eigenvalue there, the second eigenvalue to the second, the third to the third, the n to the nth, and it's the same map. T0, 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 T0. This is what I expect as a dominant term. You make it, I'm making ansatz. I'm not proving anything yet. Then it's like, okay, this would be too naive. If I prove a map, if I try with a map like this, this will not push forward this to this. So if you take this map as a T0 tensor n times map, the problem is that the push forward of this measure to this measure will never be correct. So I need to adjust. So what we do is that you say, okay, let's try then to add a term 1 over n, and then a T1, which now is a new map, which has 2 entries only, lambda 1 and lambda 2. And then you do it for all possible pairs. So, and then you make it symmetric. So lambda 2 has no meaning because it's any. So lambda 1, lambda j, and then you average over j different from 1. So this is my first term. Then I take sum j different from 2 of T1, lambda 2, lambda j, and so on. So I take a map where each component only depends on one eigenvalue and then all the others. So this is just pairwise interaction, but a 1 over n in front. And perhaps I could also go to the next order, 1 over n squared, and if I want, I could put 3 interactions. Then I stop. And then I just say, let's take this map, and let's compute the push. So let's see how much this is a transport map. So instead of giving up optimality, which was the suggestion, I'm giving up the push forward condition with a small error. So what we prove is that this map, which is just an approximate map, will satisfy this Tn built in this way. So what we prove is that you can choose this function, and maybe that function, so that the push forward of my measure, mu gamma, will be mu w plus corrections in 1 over, let's say, n cube or higher powers. So it's not the map I wanted, the density I wanted, but it's almost the density I wanted with higher correction, which means that from the point of view of computing integrals, that's as good as I want, because then the integral of psi d mu gamma, d mu w will be the same as the integral of psi composed with Tn d mu gamma plus O of 1 over n. Well, here you get, so the goal is then that you get this good enough so that once you plug in the test function you look at, here this will be a little of 1. I don't care what is the rate. In the end, I just want a little of 1 here. So I need a good power because these test functions have a lot of terms. They're not usually functions of one variable. They are usually very large in size. They grow like n to a power, this test function. So I need to compensate for this test function. But the point is that as long as I know that the error is small, I'm happy. And then with these maps now, these are very easy maps because I'm in huge dimension, but they only depend on 1 or 2 variables. So I only need then to prove regularity and property of these maps. And that's how we then got a bunch of theorems about universality in beta ensembles and so on. So the truth is that depending on the problem, you can decide what to give up. And sometimes you give up optimality. Sometimes you can give up even the push forward condition as long as you want a map which is smooth. So you can trade that. And at least in this non-commutative world where we didn't know how to work, and then we had this idea of working directly with eigenvalues, we gave up on the push forward. And then this is good. So I think I'm out of time, so I will stop here. And I thank you for the attention.